Good morning to everyone. I'm Michael Safar. I'm a researcher at NET Center and also doctoral student at the Department of Power Engineering from Technical University of Austria. Today, I want to talk about pretreatment and enrichment of biomass for thermochemical degradation. So, something about the content. The first of all, I will start to talk about the introduction to the thermochemistry. We'll move to the theory of the thermochemical process and their distribution. Then will be divided into the own thermochemical process, which are combustion, pyrolysis, torrefaction, etc. Then there will be pretreatment of the biomass, which is an important part before you start of each of the process. Then will be presented our work research from the last few years, introduce of catalytic effect of potassium, which is my part of the research, and it's the rest of the analysis what I use it for, and it's ended with conclusions of that research. So I started to introduce you to the thermochemistry, which is a branch of chemistry that describes the energy changes that occur during chemical reaction. In some situations, the energy produced by chemical reaction is actually of the greater interest to chemists than the material products of the reaction. Like, for example, the controlled combustion of organic molecules, which is primarily sugars and fats, within our cells, um, provides the energy for physical activity and other complex chemical transformation that occur in our bodies. Similarly, our energy intensive society extracts energy from the combustion of fossil fuels such as coal, petroleum, and also natural gas to manufacture clothing and furniture, heat your home in the winter, also cooling in summer, and power the car or bus to get you to the class and to the movies. So something about the nature of energy. All forms of energy can be uncovered. The three things can change to energy of an object. First is the heat, the transfer of heat. Then is work performed on or by an object, or some combination of heat and work. So the first law of thermodynamics states that the energy of the universe is constant. The change in the internal energy of the system is the sum of the heat transferred and the work done. At constant pressure, heat flow and internal energy are related to the system enthalpy. The heat flow is equal to the change in the internal energy, and quantitatively describes the energy change that occur during chemical reaction. Energy is the captivity to the work. The calorimetry measures enthalpy changes during chemical process, where the magnitude of the temperature changes depends on the amount of heat released or absorbed, and on the heat capacity of the system. It uses device called the calorimeters, which measure the changes in temperature when a chemical reaction is carried out. The enthalpy, meaning the heat flows between system and surroundings until both are at the same temperature. There is two processes. The one is endothermic, the second exothermic. Endothermic is a process in which system absorb a heat from the surroundings, and exothermic is a process in which the system released the heat to the surrounding. So The rapid increase in energy consumption and the depletion of fossil fuels have called for new energy sources and raised the interest in renewable energy generation. In view of the number of challenges, including insufficient energy resources, air pollution, deteriorated atmospheric greenhouse effect, and accompanying global warming, the research and development in the thermochemical conversion techniques is a practical and sustainable energy solution. Biomass thermochemical conversion technologies for energy generation were neglected in the past due to the low prices of fossil fuels. Nevertheless, their technologies have been revised due to the increasing energy demands and environmental concerns related to fossil fuel energy generation. These seven processes discussed are in the table are combustion, the pyrolysis, torrefaction, gasification, and hydrothermal liquefaction. We will discuss all of these processes on the next slides. This process represents the process receiving the most attention across the thermochemical platform for producing heat, power, fuels, biochars, and chemicals. All of these processes create some amount of the free products, which can be like solid, which is char or ash, liquid, which could be like BO or tar, and the gas, which is syngas or producer gas. Each process uses different reaction conditions. This is different between them, which can be like temperature, pressure, heating rate, resistance time, reactive or inert atmosphere, purge gas, flow rate, and etc. Optimize the production or quality of one of their more specific products. So the key to understanding thermochemical processing is an understanding what occurs during the fourth step of combustion, i.e. burning in the presence of sufficient oxygen. Some of all of these steps occur in the other processes, but often to a lesser extent. Most biomass contains at least some moisture, so the first step in combustion is drying. As water boils at a relatively low temperature, steam is the first thing to be removed. Fire are more difficult to get started than to maintain because water evaporation is an endothermic process, like energy requiring. So energy must be added to start the fire before any energy can be extracted from the fire. The second combustion step is volatilization or pyrolysis because no oxygen needed yet. As the heat breaks the chemical bonds with the biomass, more molecules vaporize and escape from the biomass particle. It's not until the first step, gas phase oxidation, that one sees a flame. As hot volatile molecules leave the biomass particle, they come in contact with oxygen and burn, oxidize, release heat and light. If there is enough oxygen present, the only products are carbon dioxide and water. If there is enough oxygen, however, the volatives do not burn completely and can result in heavy smoke and tar or gas phase polymerization to soot. When all of the volatile parts of the biomass have been oxidized and removed, only a very hot, slow-burning solid shell is left to undergo the final step of combustion, which is solid phase oxidation. These glowing coals, we can say, are still reacting with oxygen, but because the oxygen has to diffuse to the surface of the solid radar, then react with the gas phase fluids. The process is much slower and does not give off a visible flame. Eventually, all of the carbon is oxidized to carbon dioxide and only the non-combustible mineral material, the ash, is left. The extent to which each combustion process occurs depends on the amount of energy available, which is temperature, the amount of oxygen, and the resistance time of the biomass particle, and produce fraction in the oxidizing atmosphere. In combustion chambers and boilers, for example, high temperatures and excess oxygen are used to drive or reaction to competition. So, we start with pyrolysis. And what is it? There are several definitions depending on the source, but essentially it is a thermochemical process conducted at 400 to 800 degrees Celsius in the absence of the oxygen. The process produces gas, bio-oil, and char, and is one of the first steps in gasification or combustion. The composition of the primary product made will depend on the temperature, pressure, and heating rate of the process. And the others like reactors and etc. The pyrolysis was initially utilized to produce charcoal in indigenous cultures in South America. The material was ignited and then covered with soil to reduce the oxygen available to the material. It left the high carbon material that could stabilize and enrich the soil to add nutrients. Pyrolysis is also a process which is used to extract energy from biomass or waste, and also can be used to degrade fossil fuels based chemical. During the pyrolysis, a particle of material is heated up from the ambition to definite temperature, setup temperature of equipment. The material remains inside the pyrolysis unit and is transported by screw convector at definite speed until the completion of the process. There are some other advantages, both like economical and environmental, to doing pyrolysis, and they are utilization of renewable resources through a carbon neutral route, which is environmental potential. Another environmental potential is the utilization of waste materials such as lumber processing waste, like bark, sawdust, forests, and etc., and their agricultural residues, straws, manure. The economical potential is self-sustainable energy. The other is conversion of the low energy into biomass into high energy density liquid fuels, and the potential to produce chemicals from bio-based resources. So something what is influences this process results. There are many influences like treated material composition. Each of the major constituents of the biomass and waste feature different temperature of the thermal decomposition, which means they contribute to the results of the process in different way. Due to high diversity of material composition, it is always recommended to perform a pilot test to forecast the pyrolysis process performance in most accurate way. The temperature of the process can also influences has a major influence to the treatment results. Like high temperature of pyrolysis provide a greater quantity of non-condensable gases like syngas or synthetic gas, while on the other hand, the lower temperature favor the products of high-quality solid products for like hard shell, glycol, torrefied fuels. Um, like temperature is a factor fully controllable in the process. So thanks to electrical heated screw convector, that's all precise setup of treatment condition. So another influence could be like resist time of the material in pyrolysis chamber. This influences the degree of the thermal conversion of receiving solid products as well as the residence time of the vapor, which influence the composition of the vapors. And also the particle size and physical structure influences the speed in which material is subjected to pyrolysis. In general, lower particle size materials are quicker affected by the thermal decomposition, which can result in greater quantities of pyrolysis oil than in case of a larger particle size. So, the classification of pyrolysis methods. There are three types of pyrolysis. First is conventional slow pyrolysis, second is fast pyrolysis, and third is ultra fast or flash pyrolysis. The table and figure summarizes how each method differs in the temperature, resist time, heating rate, and products made, or major products. As you can see at the figure, slow pyrolysis is typically used to modify the solid material, minimizing the oil produced. Uh, you can see it, the content of the char is the highest of the other type of the pyrolysis. And on the other hand, fast pyrolysis is maximize the gases online produced. It just depends on the temperature what you can set up. If you want a liquid, you will set up the lower temperature, and if you want a gas phase, you will set up the higher temperature. The slow pyrolysis can yield a good quality hard shell using low temperature and low heating rate. The vapor resistant time can be around 5 to 30 minutes in this process. So it's the highest resistant time than the other two type of pyrolysis because the volatile organic fraction present in the vapor phase continue to react with each other to yield char and some liquid fraction. The quality of bio-oil produced in this process is very low. So if you want to produce the bio-oil, you will set up the fast or ultra-fast pyrolysis. Longer resistant time initiates further cracking to reduce the yield of bio-oil. The process suffer from low heat transfer values with longer retention time, leading to enhance the expenditure by higher input of energy. The fast pyrolysis in moderate to high heating rates on the other hand, and it is the most common of the methods, both in research and in practical use. The major product is bio-oil. What you can see here. And the yield if the products are liquid condensate around 30 to 60%. Gases like CO, H2, methane, or carbon dioxide, and slight hydrocarbons. It's around 15 to 35%, and the rest of the char like 10 to 15%. Ultrafast or flash paralysis and extremely rapid thermal decomposition paralysis with a high heating rate. The main produce are gases and bio-oil. It just depends if you wanna more liquid fraction, you will set up the lower temperature as the fast paralyzes. And if you set up the higher temperature, you obtain mostly the gases. Heating rate can vary from 100 to 10,000 degree Celsius per second, and rest time are short in duration. So the yield of the products are the liquid condensate around 10 to 20%, gases 60 to 80%, and the rest of the charge around 10%. Something about the pyrolysis products. And the left figure you can see pyrolysis product, and the right figure of the pyrolysis process. The pyrolysis process of the primary reactor always produces solid, like hard char, biochar, liquid, and non-consumable gases. As the liquid phase is extracted from pyrolysis gas only during its cooling down, in some application, these two streams can be used together when providing hot syngas directly to the burner or oxidation chamber. The preparation of these products depends on several factors, what we thought about before, like including the composition of the feedstock and process parameters. The secondary reactions are related to the thermal degradation of volatile oil or tar, and strong interaction occur during secondary reaction. Concerning the thermal degradation of biomaterial, most of the investigation focuses on their major components, the cellulose. The decomposition of cellulose at low temperature leads to growth of the basic compounds, monomeric volatile sugars, such as levoglucosan, resulting from total depolymerization of the cellulose, and particularly depolymerized compounds called anhydrocellulose, which are precursor of the residual solid char. Oh, something about the first of the compound, and is a biochar. Um, Biochar is a solid product obtained in pyrolysis of biomass, and it is carbon-rich and porous material which can be used for a wide range of application, along with soil improvement, remediation, and pollution control take the most important roles. As the product's biochar differs from charcoal, which is produced at lower temperatures and considered as a solid fuel, containing high quality of volatile matter. Because of higher process temperatures, the chemical structure of biomass changes, and content of hydrogen, nitrogen, and oxygen in biochar is significantly decreases in relation to carbon. In contrary to charcoal, biochar is also not phytotoxic. Biochar is mainly used in agriculture to enhance soil fertility, improve plant growth, and provide crop nutrient. As a result, it improves the overall farming productivity. It has also gained considerable attention in livestock farming as an animal feed. biochar and climate change. Something about typical biomass contain approximately 45 to 60% of carbon and about 35 to 40 of oxygen. The remaining elements are hydrogen, nitrogen, and smaller amounts of minerals. When biomass is deteriorating or burned, a significant quantity of the carbon dioxide is released into the atmosphere and contributes to the negative climate impacts that could be avoided when producing biochar instead. The biochar is a powerful tool to address the climate emergency. When biomass is subjected to the pyrolysis process, the major of the carbon remains in the solid products, together with the minerals and most nutrients. This helps to reduce the amount of carbon dioxide released in the atmosphere because it's held in the soil. So minimize the greenhouse gases while simultaneously creating an extremely fertile soil that needs no chemical adjustment. And during the production of biochar, the pyrolysis gases are considered as an energy source and help to reduce dependence on fossil fuels. So this allows to reduce the overall fossil fuel consumption and can represent a sustainable approach to reduce the greenhouse gases emission in development countries. Something about industrial approach. So what are the biochar markets? It could be like soil additives, water retention products like hydrochar, soil conditioner, nutrients carrier, soil remediation like assistant, precursor for activated carbon. It could be also used like filtration or decontamination material, also as animal feed and additive. And it's it could be also used as biochar like water retention products. Something about pyrolysis oil. It's a liquid substance obtained in pyrolysis process and substance cooling. It's also sometimes called like bio oil or biocurd. It's usually dark, viscous liquid, and it's composite of hundreds of oxygenated organic compounds like carboxylic acids, ketones, aldehydes, furans, sugars, and water. Because it's so highly oxygenated, its fuel value, energy content, it's only 50 to 70% of petroleum fuels. The exact chemical composition of bio is dependent on the pyrolysis feedstock and the conventional use. Because bio-oil is such a complex and variable mixture, characterization of its physical and chemical properties is challenging. And it is a complex blend of molecules, usually consisting more than 200 different compounds, resulting from the depolymerization of products treated in pyrolysis. Although often high heating value around 12 to 22 megajoule per kilogram. Oil from waste pyrolysis process require further treatment to ensure its stability and compatibility with existing petroleum-based fuels. Producing stable and upgradable bio-oil with more favorable properties through measures such as addition of catalyst, changes in the processing condition, and post production upgrading in the major research for now. So, something about syngas, which is also called a synthetic gas, is a mixture of molecules containing hydrogen, methane, carbon monoxide, carbon dioxide, water vapors, and as well as the other hydrocarbons and condensable compounds. It's a main project of gasification and majority products of high temperature pyrolysis we talked about before. Carrier carried on a biomass residue and waste. When produced in pyrolysis, it's created by vaporization of volatile compounds from the raw material thanks to the heat, which indicates a set of complex reaction. A high temperature pyrolysis process carried in the absence of oxygen results in production of calorific syngas at exceptional heating values up to even 46 megajoule. The most energy rich gases are obtained from the raw material featuring a high calorific value, plastic polymers, calorific fraction of municipal solid waste. Generated synthetic gas leaving the reactor is a hot mixture of condensable and non-condensable phases. The composition of such blend depends on the source of material, which is feedstock, and pyrolysis operation condition. Gases from pyrolysis typically contain significant quantities of methane, hydrogen, carbon monoxide, and dioxide, as well as high hydrocarbons that build their calorific value and make them important fuel for the chemical energy industries. Uh, in the hot state, synthetic gas contain condensable and permanent gases and can be considered as an alternative or renewable energy sources and as a fuel for high temperature syngas burners. Power generating from syngas, the main application of produced syngas is typical the generating of power or heat. This can be released either in the state alone combined heat and power. Uh, Power generating plants or through core firing of the product's gas in the large scale power plants. Syngas from pyrolysis is a combustible gas and can be used for the production of power in many types of equipment, from steam cycle through gas engines and turbines. Synthetic natural gas production, it's a high temperature process of pyrolysis, so to create significant quantities of syngas with notable concentration of carbon monoxide, hydrogen, and methane. The increase in production of synthetic natural gas through the methanization of hydrogen and carbon monoxide is increasing fast. Following the interest ATI partners with European leaders in gas transformation system, GERT gas, the objective of Alliance is construction of a pilot plant dedicated to produce the synthetic methane from waste and biogenic resources. Something about summary of synthetic gas utilization routes. It could be like heat production for drying or industrial purpose, industrial steam or thermal oil production, a replacement of conventional fuel in the existing boilers, and electricity generation via our sea turbine or, for example, steam turbine. Torrefaction, also known as a mild pyrolysis, roasting or high temperature drying, It's a relatively recent thermochemical technology in the biorenewables field. Torrefaction is achieved by slowly heating biomass at representatively low temperature, from 200 to 300 temperature, 300 degrees Celsius, sorry, in a limited oxygen environment, causing the volatilization and degradation reaction to occur. Important chemical and physical transformation occur under these conditions that produce a more hygroscopic, homogeneous, and energy-dense solid fuel source. A typical mass and energy resulting from torrefaction is approximately 70 to 80 and 80 to 90, respectively. Step by step, feed material is heated up slowly at less than 50 degrees per minute, and it's done over a period of hours to days. This way, the volatives are released and carbon maintains a regained structure. In the first stage, water, which is a component that can inhibit the calorific value of fuel, is lost. This is followed by a loss of CO, CO2, H2, and methane in low qualities. By doing this, approximately 70% of the mass is retained with 90% of the energy contained. The main of the torrefaction is upgrade the fuel characteristic of biomass such that it can be co-combusted with a coal or used as independent fuel by being pelletized and storage with little to no microbial degradation. The main difference between pyrolysis, gasification, and torrefaction is derived from their production motivation. Conventional pyrolysis and torrefaction share a similar operation condition. However, a significant difference exists in the application and composition of the products. Torrefaction is similar to carbonization in that they share the same products motivation, aiming to maximize the product of green, energy-dense solids. However, the torrefaction also aims to maximize the energy and mass yields by minimizing oxygen to carbon (OC) and hydrogen to carbon (HC) ratio. The process parameters of torrefaction also differ from carbonization. Torrefaction employs low heating rates and relatively low temperature to drive away only the low energy dense volatives and chemical bound water, avoiding carbonization reaction. Gasification is also a thermochemical process in which the reaction between fuel and the gasification agent take place and syngas is produced. The syngas is mainly composed of carbon monoxide, hydrogen, nitrogen, carbon dioxide, and some hydrocarbons, which can be like methane, ethane, ethane, and very small amounts of ammonium or hydrogen. HTO or hydrothermal liquefaction also refers as hydrolysis is a thermochemical depolymerization process in an enclosed reactor to convert wet biomass into biocrude oil and chemicals. Many of the technologies that convert biomass to biofuels require dry feedstock. However, a great deal of the wastes available are rather than wet, and drying them to make biofuels will demand huge amount of energy. Hydrothermal liquefaction is a process that uses the water and the feedstock, thus drying is not necessary anymore. This makes the process very interesting for high moisture feedstock such as organic residue and sludge. The technology traditionally used pressure mainly up to 250 bar and temperature up to 350 degrees Celsius, keeping the water just below a critical point. Uh, Recent developments by Steeper Energy in Denmark demonstrated, however, that by increasing the temperature to over 400 degrees Celsius and pressure to 380 bar, higher efficiency and more stable operation condition can be achieved. At this condition, the water alters its physical and chemical properties, which results in chemical reaction that dissolve the organic structure or of bioorganic materials and convert them to fuel intermediates. The water is not evaporated, which means that the high efficiencies can be achieved. The applied condition mimic the geological processes which were responsible for fossil oil and natural gas formation. The timeline of oil and gas production is millions of years, while the hydrothermal liquefaction reaction uses just 15 to 30 minutes. Unfortunately, this affects the oil quality, which is rather poor compared to fossil crude oil. Consequently, consequently the products called biocrude must be upgraded before it can be considered as a fuel. Given the nature of the hydrothermal liquefaction technology, several challenges still need to be resolved. The challenges are mainly material and operational associated with the operating condition, catalyst uses, as well as upgrading the products to high quality engine fuel. Hydrothermal liquefaction is under demonstrating in several countries. Like HTL, although not commercial, it seems as a very promising technology also from the techno-economic point of view. Hydrothermal liquefaction is currently under demonstration in Denmark, Austria, Turkey, and India. In Norway, has a Sylvia Green Fuel has chosen this technology for their process plant to demonstrate the project or products of renewable fuels. So something about the pretreatment of biomass waste. It's costly and affects both upstream and downstream process. On the upstream side, it can affect how the biomass is collected or harvested, as well as the community of the biomass. Downstream of pretreatment, the enzyme production can be affected, which in turn will affect the enzymatic hydrolysis and sugar fermentation. Pretreatment can also affect hydrolyzed condition and hydrolyzed fermentation. The products made and the eventual final processing also will be affected by pretreatment. However, it's more costly to not do pretreatment. There are two different types of pretreatment: physical effects and chemical effects. A physical effect disturbs the higher order structure and increase surface area and chemical enzyme penetration into plant cells walls, and include mechanical size reaction and fiber liberation. Chemical effects include solubilization, depolymerization, and breaking of cross-links between macromolecules. The individual components can swell depending on the organic solvent or acid used, and lignin can redistribute into a solution, and lignin and carbohydrates can be depolymerized or modified chemically. About technologies, we can start with the size reduction. Size reduction is also known as comminution. Decreasing particle size of biomass improves accessibility to plant cell walls, carbohydrates for chemical and biochemical depolymerization. It can also increase the bulk density for storage and transportation. And there is a cost of energy when using mechanical size reduction. Something about low pH method. The mechanism for low pH treatments is hydrolysis of hemicellulose. Hydrolysis is a reaction with the water where acid is added to the water and to accelerate the reaction time. The addition of the acid and elevated temperature increase the rate of reaction. Another is neutral pH methods. Pretreatment can also take place in neutral pH water. There are two pathways that can occur. One is acid compounds are released from acetylate aminosolubles, mainly acetic acid, and water can also dissociate as the temperature and pressure increases to near the supercritical point, and as this happens, the water behaves like an acid-base system. The key parameters are time, temperature, and moisture content, and the effect are similar to the low pH methods. The high pH method has also two possible outcomes for the chemistry behind the high pH treatment. One is essentially a degradation reaction that liberates lignin fragments and lead to lignin dissolution. And second is other is condensation reaction that increase the molecular size of lignin fragments and results in lignin precipitation. Addition of oxidizing agents greatly improves the lignification. Another is organic solvent separation. For the organic solvent pretreatment, the main mechanism involves the dissolution of lignin by organic solvent and um, representation by adding an antisolvent such as acidificate water. This method was first introduced as a pulping method for papermaking. Next is ion liquid separation. One of the more usual methods of pretreatment of biomass use ion liquid. There are organic salts that usually melt below 100 degrees Celsius and are strong solvation agents. A common salt that we are all familiar with is table salt, sodium chloride. When cellulose has been dissolved by organic liquids and then represented by an antisolvent, cellulose is less crystalline and easier to break down. And the last is biological treatments. The last technology we will look at is biological pretreatment. Lignin is removed from lignocellulose biomass through lignin degrading microorganism. Key parameters are temperature, cultivation time, nutrient addition, and selectivity on lignin. Advantages to using ecosystems such as this include no chemicals, build condition, low energy and low capital outlay, and less enzyme use later on. However, per treatment take days to weeks. So lots of cellulose and hemicellulose contain contaminants and additional per treatment for a higher sugar yield. So now we will move to our laboratory and our work and research. The objective for our laboratory is specialized in the research into the effects of anthropogenic activities in the field of thermal processes on the environment. I work on the thermochemical conversion of fuels, research and development of pyrolysis, combustion, purification of the biomass and waste, and energy recovery of waste, catalytic effects of material, and etc. I also operated mostly on FTIR, which is infrared spectrometry, TJ and DSC2, what is thermogravity analysis mostly, and laboratory pyrolysis with gas chromatography. About our cooperation, we created nice co-workers with Taiwan, Poland, and Croatia. We cooperate with Professor Chen from National Cheng Kung University in Taiwan. With him, we collaborated on the study of thermochemical methods and catalytic effects of biomass, enriched with various catalysts. With Poland, we cooperated with Częstochowa University of Technology on the project NAVA, environmental safety of biowaste and circular economic projects. And we have another interesting cooperation with Mr. Stanchin from University of Zagreb in Croatia. There we collaborate on the pyrolysis or co-pyrolysis and synergic effects of biomass and plastics. About our research, I choose this work, which is effect of potassium on the thermal degradation of biomass evaluated using thermogrammetric analysis. I choose it because we performed experiments in both pyrolysis and torrefaction and also combustion here. So we can observe and see the results from these processes. We cooperated here with the Taiwanese university, what I said before, and also with some University de Lorraine in France. Something about my introduce and main objectives. The catalytic effects of potassium on biomass thermochemical reaction are studied here. The crystallinity of cellulose decreases with increasing potassium concentration. We observe that the reactivity of biomass impregnated by the potassium in pyrolysis is intensified. That ignition temperature of treated biomass is lowered slightly, whereas its burn temperature is relative profoundly, and substantially time saving can be achieved for potassium impregnated biomass in torrefaction. We also read a lot of papers and works like before. It's a very important part on the research before we start, because you can compare it to this research and looking for something new. The main objective is that its biomass is considered as a renewable and eco-friendly energy source that contributes to the reduction of carbon dioxide emission. It can be utilized for electricity, heat, biofuels, and chemical materials via thermochemical process such as pyrolysis, gasification, combustion, torrefaction. The amount of inorganic metals ranges from less than 1% in lignocellulosic biomass to 15% in herbacellulose biomass, depending on the type of biomass and its growing condition. These inorganic metals, which indigenous exist in biomass, also influence the characteristic of pyrolytic products. The previous studies have shown that inorganic metals may act as catalytic in the thermal behavior of biomass, char formation, and pyrolysis products distribution. But there is still no analysis of the basic reaction between inorganic metals and biomass. It is therefore necessary to understand not only the catalytic effects of potassium, but also its behavior during thermal processes to be the ensure option production, better future pretreatment of biomass, and quality of the products. In this work, we studied the catalytic effect and thermal decomposition of biomass and alkyl mixtures, with a focus on the effect of potassium in biomass using thermogravimetric analysis. Potassium was added as potassium carbonate by impregnation, what we will discuss later. This type of pretreatment can improve the properties of biomass for thermal conversion by improving grindability, heating value, reducing the hydrophobic nature, and increasing resistance to biodegradation. So, the sample preparation that the biomass used in the study was rubber wood obtained from the Chinese Petroleum Corporation (CPC) at Taiwan. The raw biomass was ground by a crusher and sieved between 60 to 120 mesh. The sieved sample was then dried in an oven at 105 degrees Celsius for 24 hours for subsequent treatment. When preparation potassium enriched biomass, potassium was loaded into dried biomass sample by chemical impregnation. Potassium carbonate was chosen as the source of potassium for the impregnation. The potassium carbonate solution were prepared by mixing deionized water and anhydrous potassium carbonate according to the required concentration. Impregnation was done by putting 5 grams of dried rubber wood sample into a separated potassium carbonate solution in a break and mixing ratio of 10 mg per 10 milliliter per gram, followed by mixing the mixture using a stirrer for 1 hour at the room temperature. Afterwards, the impregnated samples were filtered and dried at 105 degrees Celsius for 24 hours, and the samples were then placed in the sealed plastic bags and stored in an electronic cabinet at the room temperature until experiments were carried out. In this study, the free low potassium concentration was prepared and were selected which were close to the concentration in another study. And to provide a more comprehensive observation about the catalytic effects of potassium on the biomass structure and thermochemical conversion, it was prepared also to higher potassium concentration, like 0.3 weight concentrate and 0.5 weight concentrate. The chemical structure of rubber wood affected by impregnated potassium under different potassium concentration has been analyzed by Fourier transform, infrared spectrometry, and X-ray diffraction, and to figure out the catalytic effects of the potassium on the thermochemical behaviors of biomass, which is by pyrolysis, combustion, torrefication characteristic of rubber wood are comprehensively studied using a thermogravimetric analyzer, where the biomass is impregnated by that potassium carbonate at different concentration what we discussed. At the approximate entire fiber and calorific analysis of the raw material were performed to figure out its basic properties. The approximate analysis was performed according to the ASTM standard procedures. The weight percentage of carbon, hydrogen, and nitrogen in the biomass were measured by an elementary analyzer, Perkin-Elmer 2400 Series 2, to accomplish the elementary analysis. The weight percentage of the oxygen was obtained by the difference that the oxygen was equal to 100 minus C bond, H bond, and N bond, nitrogen bond. The contents of imidazole, cellulose, and lignin in the biomass were analyzed following the fiber analysis. And the higher heating value, HV, of the samples were measured by means of bomb calorimetry, IKA C5000. The high heating value and elementary analysis of raw biomass and potassium enriched biomass are shown in the table. The results indicated the high heating value of the raw biomass is 15.45 megajoule per kilogram. By increasing the potassium content of the sample, the carbon content gradually decreasing, we can see in the table, from 46.69 to 45 to 65. And even with the decreasing calorific value, for example, in the sample with the content of the potassium plus 0.012, you can see that there is a 14.32 megajoule per kilogram. This meaning it's with the content of potassium decreasing the content of the carbon, and its heating value is going decreasing. Considering the changes of elemental composition, there is no significant difference between raw and impregnated biomass. So we can start with the TJ and DSC analysis. So why we choose the potassium? We choose the potassium because it's a natural catalytic in biomass thermochemical conversion and plays an essential role in plants growing. The pyrolysis, combustion, and purification of the TJ analysis, we could characteristic of the sample were analyzed by the thermochemical analyzer, TGSDT Q600 and thermal analysis instrument, and each ran around 5 milligram of sample were loaded into an aluminum oxygen crucible, and then the crucible was sent into the TG furnace. For pyrolysis and combustion analysis, which used nitrogen and air gases with flow rate of 100 milliliter per minute as carrier gases. In TGA, the raw of TJ, the raw of potassium energy biomass sample were heated from room temperature, which was 25 degrees Celsius, at the heating rate of the 20 degrees per minute to 105 degrees, followed by keeping this temperature for 5 minutes to provide a dry basis sample for the TGA experiments. And then the samples were heated from 105 to 800 degrees at the heating rate of 20 degrees per minute again. The incidental sample rate during the analysis was detected and recorded at a frequency of 2 Hz from the TGA and derivative the thermogravimetric DTG analysis curve, we will see soon, of the samples in the air. Their ignition and burning temperature were determined by the intersection method. With regard to purification, the heating process between room temperature and 105 degrees was the same as those of pyrolysis and combustion. Afterward, the sample was heated at the rate of 20 degrees per minute to the desired torrefaction temperatures. We choose 150, 200, 250, and 300 degrees Celsius, and then was held at this temperature isothermally for 120 minutes, which was 2 hours. Nitrogen was adopted as the sweep gas in the TGA at flow rate of 100 milliliter per minute to avoid any oxidation reaction during the experiments. The experiment results were fairly uniform between each run, and the relatively error was controlled at below 5%. So we can start with the thermogrameter analysis of combustion of the samples. That for the biomass combustion, the ignition temperatures of the impregnated samples are slightly lower than that of the parent biomass, whereas the burnout temperature of the impregnated material are reduced significantly, stemming from the enhancement of the combustion reactivity of the biomass. The TGA and the DTG curve of the raw and treated sample in air are shown in figure. The figure depicts that the prime oxidative or combustion reaction occurs at the temperature of 200 to 500 degrees, giving a wider range of reaction temperature when compared to that of pyrolysis figure, which we see later. Unlike the pyrolysis DTG curve, the combustion DTG curves are featured by two peaks in the case of the raw and treated material with low potassium carbonate concentration. The first peaks stem from the thermal decomposition of whole cellulose and particularly the composition of lignin. The second peaks are mainly described to char oxidation resulting from the combustion of remaining lignin or fixed carbon in the samples. This two peaks you can see on DTG like the picture on below. Overall, the temperature of the first and second peaks shift toward the lower temperature with rising potassium concentration. This can be explained by the enhanced oxidation reaction by potassium. For the sample treated at the high potassium carbonate concentration, such as 0.022, the TG and the TG curves are substantially different from those at the low potassium carbonate concentration. This is the pink, pink curve. The most reactive zone is in a temperature range of 210 to 340 degrees, mainly resulting from the oxidative reaction of the cellulose and hemicellulose, similar to the observed in figure. Small peak located at 198 degrees is due to the oxidation reaction of modified cellulose by impregnated of potassium. For temperature between 7 to 800 degrees, the peaks exhibit are presumably owing to the combustion of retinate lignin with potassium carbonate. In this, the values of ignition temperature and burnout temperature, which are at the table, and the both temperature of the raw biomass are the ignition temperature at 277 and burnout temperature at 485 degrees. The ignition temperature values of the impregnated samples are lessened to a small extent when compared to that of the raw biomass, uh, revealing the slight impact of the catalyst on the ignition temperature. Both the ignition temperature and burnout temperature of the samples are determined by the intersection methods. The burnout temperature can be considered as an indicator to stand for biomass reactivity. Different from the ignition temperature, a profound decrease in the burnout temperature with increasing impregnated potassium concentration occurs. These phenomena imply that the addition of the potassium into the biomass can substantially intensify its oxidative reactivity. In the case of potassium carbonate, uh, for 0.022, the value of ignition temperature is 198 degrees, is lowered dramatically. So for the paralysis on this experiment, on account of the destruction of the crystalline cells after potassium carbonate impregnation, its reactivity in the paralysis is improved by the cleavage of the hydrogen bond and glycosidic indicate. The paralysis Tg and the Tj curves of the raw and impregnated samples of potassium are shown in figure, and the DT curve of the raw material of the picture B is a significant peak at 366 degrees Celsius, accompanied by a shoulder at 390 degrees is observed. The peak and the shoulders are due to the thermal decomposition of the cellulose and hemicellulose respectively. The curve behind the peak accounts for the decomposition of lignin, whose level is by far smaller than those of the shoulder and peak. In regard to the DTG curve of the treated sample, the peak shifts toward lower temperature with increasing potassium concentration, and the shoulder has turned to disappear. You can see on the smaller picture inside the B picture. Due to concentration of the potassium, it's going to the lower temperature. In the case of the higher concentration of the potassium, the Tg and the Tg profiles are different, but the others. different from the others. The two significant peaks can be identified at 194 degrees and 268 degrees. 194 degrees is owing to the decomposition of modified cellulose from impregnating potassium, and the peak at 268 is due to the decomposition of hemicellulose and cellulose. In addition, a small peak can be found at 788 degrees, mainly as corresponding to the decomposition of modified lignin with dropped potassium, same as the combustion curve. At the end of the pyrolysis at 800 degrees, is found that the retained salt increases from 14.4 to 38 uh, percentage. What you can see at the end of the curve of TGA on the left picture. That raw biomass has been at the ended weight at 800 degrees with 13.4 percentage, and concentrate with higher potassium obtained like 0.022 has ended at 800 degrees with 38 weight percentage. This is mainly due to the polycondensation reaction facilitated by impregnation of potassium for char formation and more potassium retained in the biomass. The temporal TGA and temperature curves of the raw biomass at esterification temperature of 150, 200, 250, and 300 degrees are demonstrated in the figure. Meanwhile, the DTG curves versus temperature from 105 to 800 are shown in figure B to examine the thermal decomposition of the biomass during torrefaction and pyrolysis. For the torrefaction of the raw material at 150, to figure A, almost no thermal decomposition occurs. And the variation of the sample's mass is slight at the torrefaction temperature of 200 degrees. The torrefaction at the 150 and 200 are closely resemble without torrefaction. This suggests that the lower temperature of torrefaction is nearly inherited by a chemical frozen reaction. In contrast, the TJ curve reveal that the decrease in the biomass mass is obviously when the biomass is torrefied at 250 or 300 degrees. In DTG curve at 250, the shoulder disappears after torrefaction and the white of cellulose peaks became thinner. This behavior is attributed to prolonged degradation of hemicellulose and particle decomposition of cellulose. Once the torrefaction temperature rises to 300 degrees, only a flat region is found during pyrolysis, which is mainly ascribed to the decomposition of lignin. This implies in return that hemicellulose and cellulose are almost destroyed once the torrefaction temperature is as high as 300 degrees. The solid yield profiles after torrefaction are shown in figure A for the raw and low potassium impregnated samples. and one of the higher concentration of the potassium. Uh, for Their solid yields are very close to each other at low torrefaction temperatures such as 150 and 200 degrees. Especially the solid yields at the two temperature are in the range of 99%. With the torrefaction temperature of 250, a reduction in the solid yield with increasing potassium concentration is clearly exhibited, decreasing from 76% to 59 weight percentage. This arises from the fact that cellulose decomposition at the torrefaction temperature is intensified. For the torrefaction temperature of 300, the solid yield increasing at the potassium concentration of 0.012 and 0.022. This can be explained by the two mechanisms. First is the chance of biochar formation from polycondensation reaction at 0.012, and the second is relatively more potassium is retained in the sample at 0.022. To evaluate the catalytic effect of potassium on the biomass verification for time saving, profiles of required time reaching the specified mass losses of 3.5, 22.5, and 40 weight, weight percentage corresponding to the verification temperature of 200, 250, and 300 degrees are shown in the figure B. With the same mass loss at the least 28% of the purification time can be reduced for the potassium impregnated biomass, and the maximum time saving can reach 93%. Clearly revealing the catalytic effect of potassium on the thermal degradation of the biomass, it is apparent that the profile tends to go down with increasing potassium concentration, especially for the torrefaction temperature of 200 and 250 degrees. This implies, in turn, that substantial time saving can be achieved for biomass torrefaction when more potassium is impregnated into the biomass. So something for FTIR and XRD analysis, that to figure out the structure in the samples, the raw and impregnated samples were analyzed through Fourier transform infrared spectrometry (FTIR) analysis by means of FTIR spectrometer with the alternate total reflection ATIR. The FTIR spectra were recovered in the wave number range of 650 to 4000 cm-1, and 16 scans were collected per run with a special resulting at room temperature. The X-ray diffraction (XRD) analysis of the sample was also carried out using an X-ray diffractometer, and in the XRD analysis the samples were measured at the diffraction angle to alphas between 10 to and 30 degree angle. On the left, demonstrated spectra of the raw and treated samples in which the gray zones are identified as the normal absorption bands in wood material. The Fourier transform in infrared spectroscopy clearly indicates that potassium is embedded in the biomass, especially at high potassium concentration, I 0.022 and 0.036. When the samples is treated by impregnated potassium, some additional peaks appeared blue zone, altitude attributing to the characteristic bands of potassium. They are especially pronounced for the samples treated with high concentration of potassium. On the right picture, there are X-ray diffractograms of untreated and treated samples. The X-ray diffraction suggests that the crystalline cellulose at the crystallographic planes of 110 and 200 is destroyed progressively with increasing concentration potassium. So the X-ray diffraction indicated that cellulose crystallinity decreasing with increasing the potassium concentration, which increases the biomass reactivity in pyrolysis. In small peaks around 24.5 degrees exhibit exhibit that when the impregnated of potassium is higher than or equal to this enriched of potassium. This is attributed to the doped potassium in the modified samples. So, for a conclusion, this work has shown that potassium has a catalytic effect on the decomposition of biomass during thermal treatment by pyrolysis and torrefication, and also the combustion. It has been shown that weight loss is increased with an increasing concentration of potassium during torrefication. This influence was more pronounced at the torrefication temperature of 200 and 250 degrees. Overall, the results reveal that the effect of potassium can be negligible at the lower temperature of torrefication, while the torrefication at the higher temperature a significant caloric effects observed. The practical impact is that the temperature or treatment time may be reduced due to the catalytic effect and thanks to its saving energy for consumption. Moreover, the produced potassium-rich biochar is conducive to the developments of carbon storage, so amendment, and negative emission technologies. I'm very happy that we were also awarded for this research as a highly cited research paper in last year. So this was all from my side. Thank you for your attention. Now is the time for your question, and also want to say that enjoy the rest of Friday and enjoy your weekend.